we are with lesson 8 in this unit, and we're still talking about vectors in 2 dimensions. Some important things to know, though, is that very often it's much more convenient to use an algebraic approach to solve vector problems rather than using scale diagrams, right? Mainly because this is a much more accurate way to do things. We don't have to estimate using rulers, we don't have to estimate using protractors, we're not drawing sketches. This way we can actually just do some math and we can solve these problems algebraically. So essential learnings for kind of this lesson and onward is that we can take any 2 vectors and we can add them together algebraically, especially if they're perpendicular, using nothing other than trigonometry and the Pythagorean theorem. Okay, and if we use this, what we call the component method of vector addition, we can add any and all vectors, and that's really, really important. So we're going to take the time now to just recap a couple of things here. Recall that for any right angle triangle, and this is specific, it's got to be a right angle triangle, we can use the Pythagorean theorem, and we can use SOHCAHTOA, our trigonometric ratios. Okay, so that if this is our angle theta, the sine of this angle is equal to the opposite over the hypotenuse. And that's what we see here. This should be review for any grade 11 student that's taking this course, as I'm sure it is for you. Okay, so we're going to use this above information to solve vector problems from now on. And these are not simple tasks, okay? So solving vector problems is relatively straightforward if you follow what I think are four very, very straightforward steps, okay? And so that's what we're gonna talk about now. So step number 1 in any of these vector problems is to first draw a sketch of the problem. Okay, so this is an important step. It's going to kind of help you set the context. It doesn't have to be the type of diagram that we were doing today in class, where we actually have to create a scale and so on and so forth. This is just a sketch, right? Hopefully we're using a ruler, but worst case scenario, we're just kind of sketching out what we want to do. Step number 2 is that we're going to break down each of the given vectors into components. Okay, and what I mean by components is horizontal and vertical parts. Okay, so any vector can be broken into its horizontal and vertical part. We're going to show you how to do that in a moment. Step 3 is to add the horizontal components and then we add the vertical components and we say then that these 2 totals represent the horizontal and vertical parts of your final vector. Okay? And last but not least, step 4 is that now that we have an overall horizontal and an overall vertical, we find the total length using Pythagoras and the angle using trig. All right, so these are our steps overall. This is what we're going to do. And I'm going to show you kind of a complete solution following these steps as a model, okay? And that's going to come next. So, but first, this is what I want to focus on first, because we need to get through step 1 and step 2 before we can get to the meat, which really is step 3, and then putting everything back together is step 4. Step 1 and step 2, though, we have to be able to do, okay? And so let's take a look at this little example 1. This is going to go over step 1. How do we do step 1 and step 2, and what do these things mean? So first of all, break the vector 5 centimeters north, 65 degrees east into 2 perpendicular component vectors. Okay, so this is what we talk about when we talk about breaking down a vector into its horizontal and vertical components. Okay, so what we're going to do now, this is really going to illuminate step 2. And you're going to do this every single time you have one of these vector problems. So here it is. So first, let's draw a sketch. First of all, north and east. Okay, these are our 2. Here's east, here's north. And so we're going to draw our vector. Okay, I'm going to use blue. I'm going to go a little bit bigger here. All right, and so we're going to draw this vector. And of course, this is north 65 degrees east. Okay, so we're using a ruler to do this. And this is what we have. And of course, this is a sketch now, right? So, you know, we're being somewhat careful, but north 65 degrees east, that's this angle in here. Okay? And this length, the length of this is 5. Okay? So this is what we've got. Here's a sketch of our situation. And I want to break this into 2 perpendicular vectors. So this is a way to think about, another way to think about this problem is that we say, okay, to get from point A, which is right here, to point B, which is right here, I could take this displacement, right? I could go 5 centimeters, and I could go at this angle. Another way to get from point A to point B is to travel perpendicularly. So I could go straight north for a little distance, and then I could go straight east for a little distance, and I would get from point A to point B. These 2 things that I've just drawn in red, this and this, these are 2 perpendicular component vectors, right? So basically, I'm going to form a right angle triangle, and what another thing that this is telling us to do is that this is saying find the legs of the triangle. Okay, so that's basically what this is telling us to do, is to find these legs. Now, this is actually not that hard if we know trig, and you can probably already see, oh, okay, I can find these 2 perpendicular component vectors. Let's work on the horizontal component first. Okay, so we're going to go down here and we're going to say the horizontal, this little part first. And when I look at this, I know that the hypotenuse is 5, and I know what this angle is. So this is the horizontal side over here. This is the vertical side. And so the horizontal side is, of course, the opposite, right? The opposite side to this angle, which is 65 degrees. So if I'm using the fact that this is the opposite and this is the hypotenuse, then that's the sine ratio. And I would say that the sine of 65 degrees is equal to this side length, this horizontal side length, divided by 5. Okay, that's exactly what the sine ratio tells us to do. And when I manipulate this, I would say 5 sine 65 is equal to h. And I would put this into my calculator, which I'm going to do right now. 5 sine 65, and I get 4.53. So the horizontal component is 4.53 centimeters. Now, an important thing to remember, east, this is in what direction? Because it is a vector, it's in the east direction. Okay, so we're going to put that in there. All right, now the vertical component you could probably do now on your own, but let's go through it together. So when we look at this vertical component, this side of this triangle is the adjacent side. And so if we use adjacent over hypotenuse, I have cosine, the cosine ratio of 65 degrees is equal to the adjacent, we didn't call it adjacent, we called it vertical, vertical over 5, which is the hypotenuse. And so now I get 5 cos of 65 degrees is equal to v. And so my vertical vector is 5 cos 65, which is equal to 2.11 centimeters. And this would be in the north direction. So what I've done is I've taken this vector and I've broken it apart into a horizontal and into a vertical. And this is kind of the first step. Well, really, this is the first and the second step in doing a bigger vector problem. And this is how we're going to do this. So every single vector that we're given that's in this form, we need to break it into its horizontal and to its vertical components. Okay, so that's example 1. And let's continue on with now a complete question. Okay, so here's example 2, and we've got a line, and it moves 12 meters west, 30 degrees south, and then 4 meters north. Okay, and so what we're going to do is I've got west 30 degrees south. All right, so I'm going to go west in the, so here's my compass, right? And this is I'll always start like this. Here's west, here's south. Oops. North, east, and south. Okay. So west, 30 degrees to the south, is in this direction here. And you can already see that I'm going to run into problems, so we're going to move this over. And we'll go this way for 12 meters. Okay. And then I go 4 meters north. And so what this is going to leave us with is a vector, and you'll notice right here, if I zoom in, you'll notice, of course, right away, these two vectors are arranged just like we learned today, tip to tail, right? The tail of the second vector is arranged at the tip of the first vector, and my overall displacement, so my final vector, so what this question is asking me to find is the line's displacement from where it started to where it finished. So this green vector is what I'm trying to find now. And I can use this component method to solve this. Okay, so a couple things that we need to know. This right here, this angle from here to here was 30 degrees. So what does that make this angle in here? Because this is going to be a useful angle for us. This in here is, of course, 60 degrees. Okay, so that's just some trigonometry. So step 1 is done. We've drawn a sketch of the problem. We know what we're trying to find. Step number 2 is that we want to resolve each of these vectors into its horizontal and vertical components. So I'm going to make a suggestion for you. You do not have to follow my suggestion, but this is what I always do, okay? So I always do a little chart, and I say horizontal over here, and I say vertical over here. Here's vector 1, and I'm going to do the work for it. and then below it is vector 2, and I'm going to do the work for it over here. Okay, so when we go and we look at vector 1, this is this guy right here. It's this first vector that we drew. And we need to break this up, just like we did before, into its component parts. So we're going to use black, and so this vector, to break this up into its component parts, is that I would go straight south, and then I would go straight west. Okay, so these are its two component parts. You can see now why this angle of 60 was important, because that's what this interior angle is here. It's 60 degrees. And now I've got my horizontal and I've got my vertical. So here's horizontal, here's vertical. Okay, and what I'm going to say then is I'm going to say, okay, well, if this internal angle is 60 degrees, I'm going to go with the horizontal first. This is the opposite side. So I've got sine of 60 is equal to the opposite side, which is the horizontal component, over 12. And I can rearrange and I can say h is equal to 12 sine 60. And if I do this calculation, 12 sine 60, I get 10.4 meters. It's in the south direction, right? Which means if we're going with our standard sign convention, is south a positive or is it a negative value? And you should be saying to yourself, oh yeah, that's right, that's negative. So we got to put a negative sign there, okay? And so there is our horizontal component for the first one done. Let's do the vertical. Sorry, that's in the, sorry, I said south direction, but that's in the west direction. Okay, so this is of course the west direction. West is the negative. It's the negative right here. Okay, so now let's do the vertical component for this. And of course, this is going to be the cosine of 60, because this vertical right here is the adjacent side to this triangle. So cos 60 is equal to v over 12, the vertical component over 12. And I can rearrange to say that v is equal to 12 cos 60, which is equal to, when we do this, 6. And this is in the south direction. So south is, of course, negative, just as west was negative before. This is the south direction, and so this gets a -6 as well. Okay, so these two negative signs are really important. And now we go and we say, okay, well, we're done. So the first vector is now resolved. The second vector, when we come and zoom in and we look at this, here's our second vector. Okay, it's right here. And it's got a length of 4. Does this vector need to be broken apart? And you should be saying, no, this vector is completely vertical. So it means I don't have to resolve this vector. Is there a horizontal component to this vector? You say no, there's nothing. So it's got 0. It's not going east or west. It's only going north. And in that case, I just add +4. So now I'm finished step 2, which is to resolve these vectors into their components. Step 3 says, if we go up here, add the horizontal components, add the vertical components. These two represent the total horizontal and vertical parts. So if I'm going to add these two together, here they are. And let's observe. I've got -10.4 plus 0 gives me -10.4. Okay, so that's 10.4 centimeters. This tells me it's in the west direction. Here I've got vertical, and so I have -6 plus 4, which gives me -2. Again, this is centimeters, and it's telling me it's in the south direction. And so this is telling me something really, really important about this green vector. We said that this green vector was our overall. And this is where we're going to tie the algebra back into the diagram. So here's our green vector, and we're going to use a slightly different color of green to show our components. So this is one component right here, and here's the other component right here. This algebra tells us that this horizontal component, which is directed west, is 10.4 units long, And this vector, which is directed south, is 2 units long. Okay, so that's what we did all of this work for, was to solve for this and this. And now you can see, oh, holy cow, I have 2 legs of a right angle triangle. I can now put them back together and I will be able to find my overall triangle. So here's what I've got. I'm just going to redraw this. 10.4 centimeters here, and I've got 2 centimeters here. And so when I put these two back together, and this is what step 4 is that I now have a way of saying, oh, wait a second, I know how to solve this now. So I use the Pythagorean theorem to say, and let's call this is the displacement, so let's call this d, because we're looking for the displacement of the lion. So the displacement of the lion is equal to the square root of 10.4 squared plus 2 squared. And this will be 10.4, take the square root, plus 4, square root of the whole thing, and I get 10.6 centimeters as my distance. And the angle, how do you find this angle? You look at this and you say, well, I've got an opposite and I've got an adjacent, and so I'm going to use the tan ratio, and it's going to be the inverse tan of opposite 2 over adjacent 10.4. And when you do this, and this is again straight calculator work, the inverse tan of 2 divided by 10.4 is equal to 10, pretty close to 11 degrees. Okay, so all of a sudden we're at a point where we can say, hey, this lion's displacement d is equal to 10.6 centimeters, and we got to put this into some kind of an angle. If you start here, you say, okay, it's west, and you tip south 11 degrees. So west, 11 degrees south. And that is your final answer. So, like I said, when you look at this problem, it's involved. And this is only 2 vectors. We could add 3, 4, 5 vectors together. But a question like this is involved, and it takes a lot of steps, and it takes a lot of careful work. There's a lot going on in this, and that's why they're very rich problems. We're going to work for almost the entire period tomorrow on this kind of stuff, and then we're going to try a couple quizzes. So these questions to try, I would not suggest doing those today or tonight. I would say wait, because this is what we're going to do in class together tomorrow to get ready. And that was a 23-minute lesson. Holy cow.